Okay, so let's get underway. So for centuries, astronomers have always speculated that there could well be planets around other star systems, known as exoplanets. But the problem is, there was no proof, and they couldn't get any proof. That all changed in 1992, where these two astronomers, Waltzscan and Frail, discovered two planets around a neutron star. And that had two implications. First of all was, yes, exoplanets, planets beyond our solar system, do indeed exist, and that the whole planetary formation process is clearly very robust. Neutron stars is a whole different talk, but needless to say, they're pretty extreme, exotic objects with a lot of strong magnetic fields around them, and it was the last place you'd expect to see a planet. So we won't talk anymore about the neutron stars and how these guys did it. But anyway, so that was two important implications, and that was the first exoplanets that were detected. And then further to that, in 1995, these two guys, Kulos and Mayor, who won the Nobel Prize for this, they detected the first exoplanet around a sun-like star. A sun-like star meaning a star similar in size and temperature to our sun. And that had three important implications. That planets may well be very common out there. Many of them may be Earth-like, because they've already found them now. We've found one around a sun-like star. And that inspired a whole generation of new instruments and research. It was really got things kicked off. So, in particular, one of the key instruments that got going from here was the Kepler Space Telescope. And you're going to hear a lot about that tonight. We'll talk a bit about it. It was launched in 2009, but within the first year, in 2010, it discovered 6 planets in orbit around a sun-like star. And that really had two important implications. One is that solar systems are very common out there. We found another one. And that triggered the search, which really was the objective for the Kepler telescope, but in full earnest, the search for Earth-like planets around sun-like stars. And that's why tonight's talk is titled The Search for Earth 2.0. And this is part one of a two-part. It's called Discovering Planets Beyond Our Solar System. I had exoplanets in there, and I asked a few people, what do you know about exoplanets? Don't know, so I changed it. So, if there's one message that you take away from tonight, it is this. The sky is filled with a diverse range of planets, some of which will be Earth 2.0. And I'll show you. So part two, so this is part one, part two, both talks stand on their own quite happily. But part two, just to whet your appetite for next month, origins, conditions, and signatures of life. So we're going to do a bit of astrobiology, leading to what should we be looking for, where should we be looking, and what should we be looking for. But let's go back tonight. So that's 30 sleeps away, guys, in case you're counting. So we're going to go back to part one. So what you're going to learn about here, and what we're going to do is we're going to talk briefly what exoplanets are, the two main types of exoplanets. How are exoplanets discovered? We'll talk about the 5 main methods and their advantages and disadvantages and so on, and how they complement one another, and how they not only help detect exoplanets, they give us a lot of information about them. Then we'll have a look, hey, what has been discovered so far up to March the 25th, 2025? And then we'll talk about the summary and implications. What does this all tell us about these exoplanets? So yeah, what are exoplanets and where are they? There's 2 main types of exoplanets. One is the type that are already in a star system. You get a star with 1, 2, 3, 4, or 5 and plus planets around them. And they would have formed from these protoplanetary disks that they're now getting to see quite happily. So the star in the middle, and a disk forms during star formation, and the planets form in there. And that's how these guys have formed. And then there's a second group that appear to be rogue. They call them rogue exoplanets. And they're just wandering aimlessly on their own, without any attachment to any star system. They've, because of one of two possibilities, either they've been ejected from a star system, not because of bad behaviour, but because of perhaps some gravitational influence from some other planets have just quietly expelled them, tossed them out. Or possibly you had a small clump of gas and cloud that contracted down on its own with self-gravity. Instead of forming a star, it just formed a little planet. So one of those two. So they're called rogue planets. We'll talk about them both, but primarily we're going to be talking about discovering how they detect these ones here. So that's what are exoplanets and where are they? So how are they discovered? And there's a problem that's made this, a real problem, that's made this, the whole episode, the whole business of finding exoplanets difficult at times. And it is that stars are a long distance away from us, particularly the stars they're looking at. You're talking hundreds, if not thousands of light years. Remember, 1 light year is the distance light travels in a year, it's 10 million kilometres. So some of them are hundreds and thousands of light years away, so that you're talking at tiny objects way in the distance. And consider this, the light from a host star, hosting some planets, is usually up to 1 billion times brighter than the light that's been reflected off the planets, creating a massive glare. So you're looking way in the distance at this glare that's blotting out, potentially blotting out the small amounts of light from the planet. So that's been a huge problem that they've had to overcome. And how do they do it? Through these 5 methods, 4 of which are called indirect methods. So we're going to talk about all these 5, the transit, radio velocity, direct imaging, gravitational microlensing, and astrometry. We're going to talk about all of these 5 now. So first message here is these 2, transit method and radio velocity method, are by far the 2 biggest methods used. And you can see here, green is transit and red is radio velocity. These 2 spikes here is from 2 data releases from Kepler, the Kepler Prime mission and the Kepler K2 mission. So you can see them sticking up. But the bottom line is what you can see here is look how much that between the green, so the transit by far head and shoulders above the rest, and the transit as well. So it's sort of really these are going to be the first 2 that we talk about. So I just want you to have that right up front in your head, put it in context. And as I've mentioned, in particular, these 2 messages, these 2 methods here, not only do they discover exoplanets, as you'll find out very shortly, you'll see they give you a lot of information about the planets as well, its size, its mass, its density, what it may be made of, its composition, and so on. So let's talk about the transit method. And the bottom line is the transit method is when the telescopes just are really very sensitive, and they're looking out for a slight little dip in the brightness of a star far away, and a subtle brightness. How much of a dip? Up to 1/10,000th of a dip in its brightness. These telescopes, Kepler in particular, can pick up. And it's when a star is transited by its planet. So here's a star, here's the planet, and it goes across like here, and as it goes across, it just dims the light, so it's blocking out a little bit of the light from the star. And this is what they call a light curve, where you map the brightness, and you chart that against time when you're observing a star, and you see a dip in the brightness, and that's when the planet is transiting the star. So it's called the transit method. Now, the size, so what information can they get? Let's have a look at this. So first of all, the size of the dip, and I've got a little video to show you shortly about that. The size of the dip indicates the size of the planet. That makes sense, doesn't it? Because if you get a small planet across here, you're going to be blotting out less of the light. If you get a large planet, you're going to be blotting out more of the light. So that all makes sense. And the time between these dips, if you're continuing to watch, you see a dip in the brightness, just keep watching it, another dip in the brightness. The time interval between each dip indicates the orbital period, how long it's taking that planet to go around its star. And it's some very easy calculations once you know the period. You know how big the star is because that's just you look at the light and analyse the light through spectrograph. You can tell the temperature, the mass, and the size of the star. So from there, you can get an idea of how long it actually, you know how long it takes. You can get an idea of the distance it is from its planet. So you can get all that information just from a simple dimming of the star, very subtle but detectable dimming of the star, you can get, that's the information you can get. Here's just a little video, just there's no sound in that yet. I think I need to do that manually, which I will do. Okay, so here's your two planets here. On the left you've got the big one and the smaller one on the right, and look at the dips. So the dip goes down much more than the bigger, and that makes sense. Okay, so what other information can they get from there? This is the TRAPPIST system with 7 close planets. A lot of you have probably heard of the TRAPPIST system of planets, this TRAPPIST-1 system. So here's some interesting things to see. How, let's just go back to here. How larger planets create deeper dips, and yes, we've seen why that is so. And B, G, and C are bigger than the other ones here. So see the depth. This one here, these big ones here are deeper than, say, for example, this one down here. So that means they are larger. Larger orbits create longer dips as well. So if you've got one that's further out, and that makes sense. If you've got a star here and you've got a planet transiting in front of it rather closely, that will travel around a lot closer than if you've got a planet out here. It's going to be seen to be travelling a lot slower around its host star. So a longer dip also means a wider orbit as well. So you've learned from here that transiting determines the size of the planet, determines the orbital period and hence the distance from the star it is, and also the size of its orbit as well. Now the size of the orbit is very important. So it tells you whether this planet is in what we call the habitable zone. And it's a specific distance from the host star whereby the temperature is just right for liquid water to be on its surface. Too inward, too hot, and the water boils away. Too far out, and it's too cold, and the water on the surface turns to ice. And if you're looking for life in the big picture, long term, a few years down the line, you want something where there's going to be possibly, if it's got an atmosphere, it's in the right zone to have liquid water. You might tell, well, how do they know the distance out? As I mentioned, they look at the spectroscopy of the star, they can analyse the star, they know exactly how hot it is, and they can work out from there to each individual star where its habitable zone is, where that temperature is just right. They often call it the Goldilocks zone. We're going to talk quite a bit more about that next month. So that's the importance of knowing the size of the orbit, the distance from the host star. So the transit method works best for bigger dips, yes, as seen with a small host star. Now that makes sense too. The smaller host star gives you a bigger dip because proportionately a planet of so big goes across, say, a small star. It's a bigger percentage of light it's blocked out, as opposed to a big massive star and a planet going across it. It's a smaller percentage. So a small star is going to give rise to a bigger dip. A large planet will give rise to a bigger dip given a host star. If it's closer distance to the star, it's going to give a bigger dip as well. So a large planet going around a small host star, such as a red dwarf, really close, is what they call the low-hanging fruit, the easiest stuff to get. And they're called hot Jupiters usually, big gas giants that are found close to its host star. And the two telescopes we're going to look at is Kepler and TESS, the two ones very sensitive. I think I've just got a... Yep. So that's the low-hanging fruit. I'm going to look at that later on. So you want a small host star, red dwarf, say, large planet, and up close, and they're called hot Jupiters. You tend to get those, and ironically, that was the first few stars that were, not surprisingly, the first few exoplanets discovered. Now, there's a lot more information you can get. It's not just simple looking for a single dip. Let's add a little bit more in here, and in particular, they're interested in variations in the timing of that transit as well. So if there's, in particular, that's very useful for picking up a planet that's not in your line of sight, so you can't see it, but there's some telltale signs there might be another planet relatively close to the one that you are picking up. And that's with variations of the timing. So instead of just seeing a nice little dip in your light curve, regular little dip of a planet going around, you start seeing timing changes going on. So this is here, this is our model. So we've got the star in the middle, We've got our known planet here that's going round, and here as it transits, every time, transit 1, transit 2, everything's at the same time. Now, what say you have a planet that you can't see, but it's sitting a little bit further out, for example, and it has a gravitational influence on the planet that you can see, but you can't see this one. So it pulls, it speeds it up, or it slows it down, and it's a very sensitive indicator. Now, here's one here is where this planet is just the unseen one, just in front, so it's pulling the planet you can see forward. So if that's so, is the next dip going to be at the same time, or is it going to come in a bit sooner or a bit later? Yeah, it'll be a bit sooner. So here it is here. So here's your first dip, your transit 1, your transit 2. It's just a little bit sooner than expected because that other planet was pulling you forward. So when they see that, they think, oh, that's arrived a little bit sooner. That tells them there's another planet just out a little bit ahead of it. And it goes the other way too. If that planet happens to get behind it, it's pulling it, dragging it back, so it's slowing this planet down. So your dip in brightness is going to be a little bit behind schedule. Now this here is Kepler 46, which is a group of, it's got 3 planets. The third one they've only just found recently, but they found the first one with the dips, with the transit dips here. But it was another team that were going over the data, and they said, hang on guys, you've overlooked something here. Look at your timing of all your dips. They're all out, they're not in synchrony. And that was actually how they discovered there was a second planet in orbit around the host star, is just by having a closer look at the data and realised the light curves weren't matching up. So the variation is great. It's not surprising of a non-transiting planet, because you can only get this, of course, when you're in the line of sight. So who's to say there's not a planet in there that's not in your line of sight? Yep, there are telltale signs. So if it's a close orbit and it's more massive than the first one, so it pulls harder on it, you're going to get a more variation in time. Okay, now there's another one too, is a variation in the duration of the dip will give the information too. And that often will be evidence either that there's a large exomoon, which they're sort of uncertain they might have found one, or possibly a ring system blocking the light. But that's also sometimes they see as well as a variation in the length or the duration of the transit dip. And you'll also see that with a planet orbiting multiple stars, a giveaway. But they think they may have found one that doesn't meet any of these criteria, so they suspect it might be a large exomoon. They've yet to visually see it. Now, the transit method does have some disadvantages, so that's the pluses of it. The planet's orbit must be in the line of sight, as I've mentioned. The probability of a planet at 1 astronomical unit, an astronomical unit is the distance from the Sun to the Earth, 150 million kilometres roughly. The probability of a planet, an Earth-sized planet, 1 astronomical unit from a Sun-like star, of picking it up is only 0.47%. It's not easy to see out there. So you need, for that reason, you just need to observe hundreds of thousands of stars. And actually, you'll see shortly that's exactly what they have been doing. And the other one is there's a high rate of false detection seen with some host stars, in particular young stars, some like the pre-brain sequence stars like T Tauri stars. They're very, very active, so they have a lot of sun flares, solar flares, if you will, going on. They're very, very active, so they're constantly altering, fluctuating in brightness in their own right. Some of them might have a lot of sunspots going on because they're very active as well, so that'll be causing naturally intrinsic dips in brightness. They might have a flare with an intrinsic rise in brightness, so they can be very, very difficult to interpret. So, and it's for that reason that whenever they detect what they suspect is an exoplanet, in particular with the transit method, to be confirmed, it's got to be double checked with another method, usually the radial velocity method, which we'll talk about very shortly. They also have computer models as well, which they use as a method to confirm a possible detection.
Well, of course, I would assume that sunspots will be a much slower dip with a planetary transit as well, unless the star's rotating very fast.
Yeah. you can get stars too, because they do mention that in the literature. Some stars are just packed, very, very active too, some of the bigger stars. But yeah, it's less of a problem. So let's just talk about now 2 space telescopes that are dedicated to discovering exoplanets, the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, known as TESS. So Kepler, you may well have all heard of Kepler, had a very popular, so it was launched in 2009. Its sole instrument was just a photometer, so just a really sensitive instrument to measure subtle changes, really tiny subtle changes in the brightness of a star. And its objective really was to determine if exoplanets are common in the galaxy. Its prime purpose was just to stare at one patch of the sky, about 105, I think it was, square degrees, just in the constellation of Cygni and Lyra. Just focus totally on that, go deep, keep it narrow and just go deep and see how many in that small region of the sky, how many exoplanets are there, just to find out, get a taste of how common are they and how common are Earth-sized planets around sun-like stars. And that was its prime mission. During its prime mission, it observed 150,000 stars simultaneously. Check that out. Yeah, so when I mention those statistics, you've got to look long and hard to find what you're looking for, but it looked at 150,000 stars simultaneously. Now, that was with its prime mission, and then 2013, so that's 4 years later, it had problems with 2 of its reaction wheels, where it could no longer keep it focused on one part of the sky. So they moved it around and looked at different segments of the sky, and that was called the K2 mission. And you saw the 2 peaks there earlier on in the incidence of the 2 data releases from Kepler, and that's those 2 missions respectively. So what has it done? It's had over 2,700 exoplanets that it's detected and had confirmed. So that's certainly a pretty impressive number. And it ran out of fuel in 2018 of propellant, so they just switched it off. So it's the sensitivity. It could measure changes in the star's brightness to 0.01%. So that's 100th of a hundredth. So that's 1/10,000th. So if a star dipped in a faraway star, hundreds of light years away, dips just 1/10,000th of its normal brightness, Kepler picked up on it, while looking at another 999,000 stars. It's capable of detecting Earth-sized planets transiting sun-like stars. That sensitivity is sufficient to do that. And here's just a little, just a 3-minute video, just a little bit about it, just to give you a better idea of it. It's on.
NASA's Kepler Space Telescope was the most productive planet-hunting instrument ever built. Of those 3,708 planets discovered so far, Kepler turned up 2,342 worlds. Kepler was launched back in March 2009 and began operations on May 12, 2009. Kepler was placed into an Earth-trailing orbit around the Sun with a period of 372.5 days. With a longer year, the telescope slowly drifts behind the Earth by about 25 million kilometers per year. It uses 1.4 meter primary mirror to observe a 12-degree region of the sky. Just for comparison, the Moon takes up about half a degree, so a region containing hundreds of times the size of the Moon. As I mentioned earlier, Kepler was designed to use the transit technique, searching for planets passing in front of their stars in this very specific region of the sky. While previous exoplanet surveys had only found the more massive planets, Kepler was sensitive enough to see worlds with half the mass of Earth orbiting other stars. And everything was going great until July 14, 2012, when one of the spacecraft's 4 reaction wheels failed. These are gyroscopes that allow the spacecraft to change its orientation without propellant. No problem. Kepler was designed to only need 3. And then a second reaction wheel failed on May 11, 2013, bringing an end to its main mission. What the Kepler engineers came up with is one of the most ingenious spacecraft rescues in the history of spaceflight. They realized that they could use light pressure from the sun to perfectly stabilize the telescope and keep it pointed at a region of the sky. This allowed Kepler to keep working, observing even larger portions of the sky, but its orbit around the sun would only let it watch one region for a shorter period of time. Instead of scanning sun-like stars, Kepler focused its attention on red dwarf stars, which can have Earth-sized worlds orbiting them every few days. This was known as the K2 era. And during this time, it turned up an additional 307 confirmed and 480 unconfirmed planets. But Kepler is running out of time now. About a month ago, NASA announced that Kepler's almost out of fuel. This fuel is important because one important maneuver it needs to make is to point itself back at Earth and upload all the data it's been gathering. NASA figures that it's just a few months away now, and when it happens, they'll instruct the telescope to point at Earth for one last time, transmit its final data, and then shut down forever.
Yep, that was 2018 that they did that. So it's worth visualizing that. That's a very productive telescope.
NASA.
Okay, so next one is TESS. TESS was these, came in after that, and it was operational in 2018, launched in 2017, operational in 2018, and it's still working in progress. So instead of initially designed for its prime mission to focus in one patch of the sky, this does an all-sky survey of the brightest stars near Earth over the first 2 years, and then it does shorter surveys from then and just constantly around the night sky. So it's focusing on G, K, and M type. They are spectral type classes of stars. To give you an idea, is G, that's our sun, is G, so all the hotter ones are so on F, O, and B, and A. Then there's K and M, so you're getting cooler down to K and M are red dwarfs. So from our star brightness and heat, going down to cooler suns. So yeah, sun-like stars and cooler. Up till last week, 605 new exoplanets confirmed. They estimate there's up to 7,000 in their database yet to be confirmed. That's been that productive, finding exoplanets. Yeah, pretty impressive. So sensitivity, it could measure changes in a star's brightness as small as 0.02%. So not quite as bright as Kepler, but remember, it's not going the distance. It's just focusing on bright stars near Earth is what it's focusing on. So it's capable of detecting Earth-sized planets, even down to 0.8 radius of Earth radii, planets transiting red dwarfs. Did you notice they commented it's focusing on red dwarfs? Because once again, that's the low-hanging fruit. Those get that smaller host planet. And red dwarfs make up about 75% of all the planets in the galaxy as well. So they're more common. So they really are low-hanging fruit. So that's what that's the sensitivity of it. So quite sufficient. So here's once again some implications of what it's doing. The implications of having repeated surveys. Since 2018, it's completed 8 full surveys. So it improves its ability to pick up a wider, diverse range of exoplanets, because instead of just moving on to one area at a time, or focusing, you're missing stuff out to the side, or you're missing something time-wise in that one area, it's constantly searching the sky. So they're going to likely get a diverse range of exoplanets. But you'll also start picking up exoplanets with longer orbital periods in time, because you might just, some planets take years, many Earth years, to go around its host star. So you do your survey over 2 years, then you go back and do it again and again, and they're constantly comparing the data from each individual star with the previous survey. So they're able to pick up, oh, there's a transit again. That's the same type of planet we picked up. Yes, it was. That was, 4 years ago. So they're able to pick up longer transit times because of that surveying the whole sky continuously. And the implications of observing near and bright stars, it enables the follow-up observations with other telescopes, for example, the James Webb. So they might see, oh, that's a star of interest, and it's nice and bright and near. So in a ground-based telescope or the James Webb Space scope can focus in on it and have a closer look at it. Look at, has it got an atmosphere? If it has, can we identify the composition of the atmosphere? Because it's close and it's bright. It's not some dim, faraway star that has everyone still guessing. So that's a big advantage of it as well. So TESS has been very, very productive. And here's just a little video just on TESS.
In the last few decades, we have found thousands of worlds around other stars. A new NASA astrophysics mission will help us find many more.
TESS, the Transiting Exoplanet Survey Satellite, is NASA's newest exoplanet mission. It's being led out of MIT, and it's going to find thousands of new planets orbiting bright nearby stars. And it's going to build upon the legacy of the Kepler mission, only it's going to focus on nearby bright stars that are sprinkled across the whole sky, and it's going to help us answer a really important question, and that is, which of our near-stellar neighbors has planets?
During its 2-year survey, TESS will look for signs of planets, ranging from Earth-size to giants larger than Jupiter. TESS will search for these new worlds, or exoplanets, using transits, the same method as the Kepler mission. As a planet passes in front of its star, it blocks some of the light, causing a slight drop in brightness. TESS can detect those subtle dips and even use them to determine some basic features of the planets, such as their size and orbit. Each of TESS's cameras has a 16.8 megapixel sensor covering a 24-degree square, large enough to contain an entire constellation. TESS has 4 of these cameras arranged to view a vertical strip of the sky, called an observation sector.
The coverage of the TESS cameras is unprecedented in terms of the amount of sky that they can actually see at any given time, and also their ability to cover such a broad portion of the sky. The types of targets that TESS will allow us to find will enclose essentially all of the bright nearby stars.
TESS will watch each observation sector for about 27 days before rotating to the next one, covering first the south and then the north, to eventually build a map of 85% of the sky. This coverage, about 350 times what Kepler first observed, will make TESS the first exoplanet mission to survey almost the entire sky. TESS will fly in a highly elliptical orbit that maximizes the amount of sky the spacecraft can image, and is carefully timed with the orbit of the Moon. It will spend most of each 13.7-day orbit collecting data, and then, as it passes closer to Earth, it will transmit that data to the ground. Because TESS's observation sectors overlap, it will have an area near the pole under constant observation. This region is easily monitored by the James Webb Space Telescope, which allows the 2 missions to work together to first find and then carefully study exoplanets. Since most of the exoplanets found by TESS will orbit bright stars, missions like Webb will be able to measure the spectra of starlight absorbed by the planet's atmospheres, which can indicate what they're made of. Ground-based measurements of the TESS exoplanets can determine their masses. Combining the masses with TESS's size measurements reveals densities, allowing scientists to better understand the exoplanets' compositions.
The thing that we're really excited about with TESS is the way that it'll actually build on the momentum that we started with Kepler. So TESS is going to take that same search approach, but apply it to the vast majority of the sky, which still hasn't really been looked at in detail when searching for exoplanets. And by focusing especially on planets that orbit bright nearby stars, TESS allows us to start looking at things like planet composition, atmospheric makeup. And that'll then be crucial when we want to start looking around stars that are even further away and in deeper parts of the galaxy as well.
TESS is the vanguard of a new era of exoplanet study and will forever expand our understanding of worlds beyond our own.
So you can, that's a good, nice little summary there of both Kepler and TESS. You really dominated the transit method. Now, actually, here's a little video. See the little twinkling star? This is a very short video. This, see it up here? I'll even go back. Because that's, you might sort of, we're constantly looking out for these little light curves. But this is, what does the telescope see? Here it is. little star. I'm going to go back. Just that's the sort of stuff, except far more subtle than that, of course. But that's what it's picking up, 150,000 simultaneously, stars. That's the information that they get, what's going on. It was giving them information just through flickering of a star. Okay, so that's the transit method. Just moving on to the radial velocity method, which is the next most common method. And that's all based around the concept that visually what we see is, you see a star here and planets appear just to orbit around the star. That's a very simplistic view of it. What's happening is the star and the planet are both orbiting around the common centre of gravity, which just because of the sheer bulk of the star relative to the planet, that centre of gravity happens to be inside the star. So the star's not stationary and the planet's going. What's happening? They're both going around that centre of gravity, but the star just appears to do a very subtle wobble, and emphasis on the word subtle, but it's just the star's doing a little, and this is an exaggeration just to prove the point, but there's the centre of gravity here with the red cross, and there's the star. They're both going around it, but the star appears just to be doing a bit of a wobble, but of course it's a lot more subtle than that. But that's all based on that principle. So there are times, if we're down here, say, when the star is neutral, see it's going away from me, it's coming towards this, going away, so it's going backwards and forwards. And that's called your radial velocity. So what they do is they point their spectroscope on their telescope towards the star, and the spectroscope splits the light into all its various wavelengths, which we perceive as light, so much like a rainbow. How light gets split into its different colours, and that's called your spectrum. So that's what a spectroscope does. But in the atmosphere of the star, between the light leaving the star and it goes through its atmosphere, in the atmosphere there's a lot of different atoms in there, elements, in particular hydrogen in particular, and that hydrogen absorbs the light at a known and specific wavelengths that they know very, very well, and so they call them absorption lines. So in the spectrum they call them absorption lines. And they're very specific and they're very known at what wavelengths they are. So when they look at a star that's doing the so-called wobble, and if we're here, currently the star doing its little wobble, here's your planet, here's your star doing its exaggerated wobble, but here it's pretty neutral and the light's just coming to you and has your normal spectrum with the spectral lines in their expected places. But in this situation here, the sun's doing its wobble away from us, so the light waves are getting stretched out like that. And when that happens, they call it redshift because the spectral lines all move a little bit over to the left-hand side. You can see that here. See, here's the double lines here, for example. They're further over here. Then it's in a neutral position here, so you see the spectrum, its normal places again, the absorption lines, and normal expected places. And then this part of the wobble, the star is doing a very subtle movement towards us. That's called radial velocity. Away from us, towards us in that direction is called radial velocity, hence the name. And the star's doing part of its wobble, it's wobbling towards us, so the wavelengths of light get compressed, and it's called blue shifted because the spectral lines all get shifted slightly to the bluer side. So that's what it's all based along. Yeah, the wobble stretches and compresses wavelengths, which is seen in the shift of the spectral lines. Now, the radial velocity, so they can measure from there's some very simple formulas, and I'll show you the graph shortly how they do it, but the radial velocity, how fast it's coming towards us or away from us, is directly proportional to the amount of blue shift or red shift in those spectral lines, those absorption lines. And it's a very simple, straightforward formula that they can work through. The velocity, the radial velocity is just the alteration in the wavelength divided by the actual wavelength of the hydrogen times the speed of light. So that tells you a very straightforward way of saying there's been X amount of movement of our lines, and that tells us it's going so fast away from us or towards us. So, what planet and star factors give the largest signal? Well, once again, it's the larger planet. Exact. Where have you seen this before? Low-hanging fruit. Where have you seen this before? With the transit method too. It's your small stars, because they're going to get influenced more by a larger planet, so they're going to have a bigger wobble that's going on, and also close orbits. And what do you call, these big, massive gas giant that's really close to a small star? They call them really hot Jupiters. Hot Jupiters. Yeah, and so it's no coincidence that the first stars that were all the first exoplanets rather that were all discovered around these host stars were all hot Jupiters. So here is what one of the graphs would look like. So here's zero radial velocity, in other words, it was in that neutral position, and here's your velocity going towards us, going away from us, and you can see it just fluctuating backwards and forwards in this nice sinus curve here. And of course you've got time, number of years here. So they can analyse that, look at the velocities concerned, and estimate it exactly from how much the waves have, the absorption lines have moved. So a higher radial velocity indicates a higher mass, so they can tell the mass. Remember, you can tell the size of a planet by the transit method, by how much it dims it. This one tells you how much of a wobble is going on, how much of a wobble is it putting onto that star, and that tells you the mass. Once again, as I commented before, if you know the mass, you know the volume from the transit method, you can work out its density from there. And from the density, you know its size, you get a fair idea of its density. You can usually work out from there whether it's probably all rock, whether it's all gas, or whether indeed it's an ocean world with a lot of water on it. They've got computer models and simulations that do those sort of modelling. Now, there's a lot of other stuff they can tell as well. The frequency of the sine waves, how often it curves, that makes sense. It reveals the orbital period, which they can from there work out the orbital size. That's just like the dips that you saw in the transit method, how often that particular signal occurs. That's easy enough. But this is interesting. The deviations from the sine wave, so instead of going up and down like a normal sine wave, if you suddenly get going up at a slope and down at a different angle and up and so on, deviations from a nice smooth sinus wave reveals the eccentricity or the shape or the degree of ovalness of an orbit. So if you've got a nice circular orbit, you've got your host star here, you've got your planet going around in a nice circular orbit, you get a nice sinus wave. If you get a highly elliptical orbit or oval orbit, you've got your star here. As the planet zips around, when it's closest, it always travels a lot faster around here. So you get a higher radial velocity. Out here, it's a slower one. So you tend to get a bit of a warped sinus wave or a deviation in the sinus wave. And from there, they can calculate the degree of oval, how oval or eccentric the shape of the orbit is. So you can work out the size. If there's other planets, you can work out the size of the orbit, that distance from the host star. You can work out the mass. You can work out the density. Computer modelling to work out the composition of the planet. You can even work out the nature of its orbit, whether it's circular or whether it's elongated and how much. So these are all the information they get from these basic detection methods. So there's currently two high precision spectrographs that are dedicated purely to radial velocity measurements. Accuracy, yeah, it's precision stuff, all right. You're just talking in tiny, tiny little motions, very tiny. I'll show you shortly about that. So the spectrographs are all sealed, super cool tanks. They use a thorium lamp as the reference spectrum. Thorium is very good because the spectral lines are very narrow and well spaced apart. So it's a very good to have as a reference spectrum. It's all about precision and accuracy. So once again, they've got acronyms for everything. So the HARPS one, both of these, which you're going to learn at, HARPS and Expresso, are in the European Southern Observatory in Atacama Desert in Chile. So the HARPS will detect signals as low as 54 centimetres per second. The Expresso one can go right down to precision of 30 centimetres per second. In other words, a wobble of a big star just moving 30 centimetres in 1 second, light years away, could be picked up. To put that in perspective, 30 centimetres, put in perspective, the diameter of our sun, 1.4 million kilometres. And these guys are picking up a movement of 30 centimetres in these stars per second. That's the just crazy precision of these instruments.
What's walking speed? Similar, is it?
Yeah. So current technology can detect super-Earths around low-mass stars. They're able to, you know, the super-Earth, it means a planet that's a little bit bigger than Earth, 1.2, 1.4, 1.5 or so times the size of Earth. So it can pick them up. They're not quite accurate, and you need about 10 centimetres per second to detect an Earth-sized planet around a sun-like star. The technology is getting there. Here's just, actually I've got a little video, it looks like a 3-minute video here. This is just about HARPS.
Astronomers using ESO's leading exoplanet hunter, HARPS, have today announced more than 50 newly discovered planets around other stars. Among these are many rocky planets not much heavier than the Earth. One of them in particular orbits within the habitable zone around its star. In this episode of the ESOcast, we take a close look at another major exoplanet discovery from ESO's La Silla Observatory, made thanks to its world-beating planet hunting machine, HARPS. Among the new planets just announced by scientists, 16 are super-Earths, rocky planets up to 10 times as massive as Earth. This is the largest number of such planets ever announced at one time. A planet in orbit causes its star to regularly move backwards and forwards as seen from Earth. This creates a tiny shift of the star's spectrum that can be measured with an extremely sensitive spectrograph such as HARPS. In their quest to find a rocky planet that could harbor life, astronomers are now pushing HARPS even further. They have selected 10 well-studied nearby stars similar to our Sun. Earlier observations showed that these were ideal stars to examine for even less massive planets. After 2 years of work, the team has found 5 light super-Earths around 3 of the stars. These planets are very good candidates for future observations looking for evidence of life. One of the newly found planets, named HD 85512b, orbits inside the habitable zone. This is the narrow area around a star where water can exist in liquid form. Astronomers estimate that liquid water could possibly be present on this planet if it is a rocky world that has more than 50% cloud cover. By looking carefully at the results from the first 8 years of HARPS observations, the team has found that around 40% of stars similar to the Sun harbor at least one planet lighter than Saturn. These new results lead astronomers to believe that they could soon find more super-Earths in the habitable zones of their stars with HARPS. These planets will be great targets for powerful future telescopes to try to study their atmospheres, looking for evidence of life. Thanks to HARPS, the search for another Earth elsewhere in the galaxy is picking up pace.
Yep, so that's another little insight into what's going on and the instruments they use. Yeah, the future, they want to get down to 10 centimetres per second, and this is where the future lies. There is 4 new spectrographs coming online in the coming years, which hope to achieve that. So that's radial velocity method. Moving along to direct imaging. So up to now they've been sort of indirect imaging. This is direct imaging, and it's best done with 2 factors. One is what they call a coronagraph, and that's putting essentially a big disc on your telescope, put it in front of the host star, the image of the host star, to get rid of the glare that's going on. And with infrared sensors to pick up the infrared heat that's coming out of planets. Planets give out infrared heat. So that's how they managed to do that. And of course, the telescope that the famous telescope that's good for that is the James Webb Space Telescope. Nice infrared, high resolution, nice infrared. So it's the intense glare, as I mentioned, it blinds the view of the planet. So you use a coronagram to block the glare. The James Webb is very good with its infrared detection. So what planet's easy to detect? You want a large planet, because it's going to give out more infrared heat. You want this time, instead of a planet being close up to the star, you want a planet that's further out, away from the glare. So you can already see how there's different methods starting to complement one another. And you also, a large one is hopefully is hot enough, and if it's young enough, young planets are good, to emit enough infrared radiation for the James Webb to pick up. And here is a star system here where James Webb has picked up 3 planets. Now you'll notice that they've all got letters after them as well, and small letters. They always start in the order at which the planets were discovered. A refers to the actual host star, and then B, C, D, E, and so on with the alphabet is the order at which the stars are discovered. And that makes sense. Otherwise, if you put them in order, the further they out, and they get discovered in different orders, it gets really messy and confusing. So they order them there in terms of their discoveries. So, and then very recently in the news, James Webb, again, it's just ideal for direct imaging. It picked up another star. And notice how this star, from the other ones were further out. This is 16 AU, astronomical units. So it's closer in. So you can see why it was the last one to be discovered. There could even be ones further, and they can't see it. But these ones were, once again, the more lower fruit, hanging fruit they could pick up, and they've just recently picked up the E planet. While the James Webb is there, once again it sees an infrared. It's designed to have a look at the exoplanets, their atmosphere, to see if it's got an atmosphere. If it's a rocky planet, has it an atmosphere? If it's a gas giant, what sort of gases are more prominent in there as well? And as I mentioned, it's ideal for very young stars, maybe up to about 30 million years old, that are still very relatively hot and giving out lots of infrared. And looking at and doing that spectroscopy, that the James Webb, having a look at sort of metallicity, that's how much elements are in it, heavier than hydrogen and helium, that have come from previous generations of stars, and also its gases, carbon monoxide, carbon dioxide. That gives them a lot of information of where and how the planet might have formed. So a lot of information they can get from that direct imaging. Then there's gravitational microlensing, the next method. And this all goes back to Einstein's general theory of relativity from 2015, who he predicted this would happen. And his concept is that any sort of mass in the universe warps the fabric of space-time around it, whereby if you get a perfect line of sight like that, you get what we call a lens or gravitational lens, where from this background star, as the light diverges out like that, spreads out, and if it happens to go through some space-time here that's warped and distorted in the shape of a lens, the light then converges back again to a viewer here who happens to be in the line of sight. So it acts as like a lens. It magnifies the image. So if you've got a star here, it gets if you've got a star here, that magnifies the light in the star in the background. You might think, well, how can they pick up planets? What's this got to do with planets? Absolutely. This is just a diagram, just explaining that again. So here's your line of sight. Here's your lens, your star in the foreground. It's quietly moving across. Star in the background appears to be stationary because it's so far back. The foreground star is moving relative. So it comes across. When it gets into your line of sight, you get a lens effect. So this light here that's going from the background star gets split up like a lens and magnified. And then this carries on again. So you can see it's a transient event. And now, if the star here, so here's just a normal star without, say, a planet, or the planet's not in your line of sight yet, you can see as it moves in front of the background star, the light of the background star increases, brightens up, just like that, okay? Now, if there's a planet going around the star, you get a second dip. And they've put it over here. If the planet's over here, you're going to get the second, well, not really a dip, it's a rise, a second peak in brightness, because you're getting two lens effect. You're getting a main gravitational lens effect, and then a smaller, shorter one from the planet going around the star. There it is here, once again, going around. Here's the star the magnification of the background light by the foreground star, and the foreground planet gives a second little spike in there. So you are just talking days, so it's a very transit event for a few days, and it's only maybe for a few hours that you can pick up the exoplanet there. Now, Steve and Grant, there's a few people in this room aren't involved with micro-lensing, gravitational lensing in the projects. We'll probably tell you more about that. But the survey's involved, so obviously to get more transits, you want to look at a patch of field in the sky that's really thick and dense, with as many background stars as you possibly can. You get your chance of one of them getting transited by a foreground star is higher. So they tend to go for fields towards the galactic bulge. The telescopes, and this is the MOA one, the gravitational micro-lensing astrophysics for astronomy. That's what's called MOA. That's dedicated down the South Island. They will monitor tens of millions of stars simultaneously, just constantly looking at all these background stars. They're constantly scanning and trying to pick up any increase in brightness of one of those background stars. Exposures, up to sort of 2 or 3 minutes, and a cadence, that's how often do they do those exposures, every 10 to 20 minutes. And they're constantly, it's obviously, I'm sure it's computers in these days, AI, and so it would be picking up on it all. So there's 4 important advantages of this. So they're not very common, and you've got to wait a long time, it's a disadvantage, but the advantage is, when it does occur, it can detect fairly low mass planets, like even Mars, as opposed to, remember, the transit method and the radial velocity method need big planets, so this can pick up small planets. It can detect planets in wide orbits. Once again, those first 2, likes narrow, short, small orbits. This one, like direct imaging, it likes an orbit further out. Its ideal one is about 1 to 10 astronomical units out to about the orbit of Saturn equivalent, because it keeps these 2 peaks more separated here. So here's the peak of the star, here's the peak of the planet, and you can see it's separated more. So that's the sweet spot for looking out for exoplanets. These, once again, this is a big advantage, because the orbital periods, if you get something like Saturn that's so far out, its orbital period takes so many years, the transit method's not going to pick up its second transit, or it's the second wobble of the star. So they struggle with this. But once again, they're all different, they complement each other. So this method will, and along with your direct imaging, is good for these wider, longer orbits. It will detect planets in face-on orbits, so you're not having to wait, to try and get everything all in line. So like you have to do with the transit. So that's very useful. It can detect planets really far, or planets around stars really long distances, tens of thousands of light years away. So it's very sensitive. And those sort of distances, you're starting to get beyond the reach of your transit and your radial velocity methods. That's the MOA Observatory down at Mount John in Canterbury, or the Mackenzie Basin, I should say. So we have it the future. So the Roman Space Telescope, which is due to see first light in 2027, all going well. Part of its mission is to do exactly this, look for gravitational micro-lensing. It's very increased resolution, highly sensitive sensors on board that'll be able to pick up smaller and rogue planets as well. And of course, it's infrared sensors, which is going to be very, very useful for picking up not only your gravitational lensing, but also direct viewing as well. And it'll be the direct viewing that'll be useful for picking up these rogue planets. And it's going to have a coronagram, as I mentioned before, for direct imaging. So it's going to have a coronagram and increased resolution and sensitivity and infrared sensors. And those 3, that combination of 3 new technologies, it will be very, very good at picking up these exoplanets. So that's where the future lies for gravitational microlensing. The 5th one is astrometry, and astrometry refers to the position, measuring and identifying the exact position of stars. And this is the same principle as the radial velocity one, in that it goes by the wobble. So the radial velocity was, as a star is wobbling, it was more interested in the radial, the to or away from us component of the wobble. But of course, if it wobbles in all directions. So there's a very subtle sidewards wobble as well. And of course, that is going to affect the position. Subtle, tiny, yes, but once again, that you're dealing with all these really fine measurements. The Gaia telescope was very useful for this. but it's which I'll come to shortly. It's finding exoplanets in distant orbits is very, very useful, ones that are further away. Finding exoplanets that do not fit in our sign of light, which the transit method relies on. And because you're looking at the wobble, how much mass the star is, how much it's wobbling, you can determine the mass of the exoplanet as well. I'll put there, yeah, that's the Gaia Space Telescope launched by the Europeans in 2013 and just last year was retired. So that was very, very precise measurements of exact positions of stars, and that picked up quite a few of these as well. So it's just moving along. So those are your 5 main methods. There are bit more detail with a few lesser common, but they're your 5 important ones. Their respective features, as you've learnt, complement each other. This is how they're matching up with discoveries. So 75% of them have been made with the transit method, by far the commonest, followed by the radial velocity, and just small numbers here with these other 3. But nevertheless, they are important because you get other properties, or they pick up on exoplanets that those first 2 would never have picked up on. 94%, there you go. So yeah, as we've talked about, one of the main themes of the talk has been combine results from the different methods give the best information about the planetary system. Its size, its mass, its density, its composition, the nature of its orbit, and so on. So that's how exoplanets are discovered. What have astronomers discovered so far? What actually is out there that they have discovered? Let's find out. So the big numbers, this just as of last week, 5,867 confirmed exoplanets that have been confirmed with a second method, and 4,377 planetary systems, indicating that almost 1,000 actually have multiple planetary systems. So almost 1,000 stars that they've picked up on have more than one planet, have essentially solar systems. The big question, how many of these rocky planets are they picking up? We're going to be searching for Earth 2.0. 67 confirmed rocky planets in the habitable zones of the host stars. Of course, they're yet to determine whether they indeed have got atmospheres and so on, and the nature of the stars, which we're going to talk about next month, about some of the problems that you have with some of the star types. Up to half of the Sun-like stars, that's our G class, that's sort of roughly temperatures between sort of 5,600 degrees, surface temperatures and the size of our Sun, half of those host potentially habitable planets. Habitable meaning the conditions for life, which means it's got to have an atmosphere and surface liquid water, but potentially habitable. They're in the right zone and they are rocky. And the other one is the exoplanets come in a wide range of sizes and orbital periods, and I'll show you. So this here is a graph. This is the data. Oh, actually, let's go back. So this here is a nice little table, a graph, showing the sizes of the planets in relation to, here's the size of Earth, size of Neptune, and the size of Jupiter. And here's its orbital period in days. Notice that's exponential. So you can see that there's a huge range of sizes of the actual planets and also the orbital periods, the size of their orbits. Now put here, this data, actually let's talk about the size of Earth here. So you're going down a third of the size of the Earth, right up to 45, actually that's 45 times the size of Earth up to here, much bigger than Jupiter. So there's a huge variation in the size. The orbital range goes from way down here is 1/10 of a day, so it's about, so roughly say 2 hours, out to 100,000 days, and Earth takes 360, just putting that in perspective for its orbital period. So huge, some tiny little rapid orbits, but some huge long ones as well, with a huge range of planets. Now this data is 2015. The only thing that would have changed in the last 10 years is the number of dots on there. The principle has not changed. Huge range in size of planets and the size and nature of their orbits. In terms of sizes, just breaking it down, about a third, 30% of the exoplanets they found are these big gas giants up there with the size of Jupiter, and the rest are relatively small, down to sort of Neptune being about the Neptune size being the biggest, Earth size, and these super Earth, which is up to 1.5 times the size of Earth. They call them super Earths. So these are considered sort of more in the smaller realm, and they make up 70%. Hot Jupiters we talked about hot Jupiters before that are really, really close. So we'll talk about that shortly. That really confirms the theory of planetary migration. You might think, how did those hot Jupiters get in there? They formed further out and moved inwards. You saw that in the last slide previous. Now this is interesting. So as you've learned that these relatively planets size of Neptune and below make up about 70% of all the exoplanets, so small planets are more common than larger ones. But there's really cool thing that's come out of here. So here's the incidence, the numbers, and it goes up like this and up like this, down like this. And look, there's more, okay, there's 2/3 more here. But look, you've got two peaks. You've got two peaks here with a gap in between. So the two peaks is about 1.3 Earth radii and about 2.6 Earth radii, what they're called mini Neptunes, because they're not those sort of bigger. These are called super Earths, much bigger than Earth, and these ones here are called mini Neptunes. But notice there's two peaks with a gap in between. When they first discovered that, they thought, wow, that's interesting. Why is that so? Why have we got this gap going on there? And the other interesting thing is that the sizes where these two peaks are, our solar system has none of these. So we're very learning that our solar system is not typical. We've got a solar system, there's others out there, but they all vary so much, and there's sort of ours is no template for other solar systems are out there. So we don't have anything. We just have a number of small rocky planets and some larger gas ones, with the Neptune being the smallest of the gas or ice giants. So why is that so? One possibility, and I mentioned planetary migration, is that planets do migrate. Some of those outer planets with a bit of resistance against the interaction with the protoplanetary disks, they'll often migrate. And there's good evidence to suggest what we call the grand tact hypothesis, whereby Jupiter early on started migrating inwards. And eventually it got to where Mars sits. And in the meantime, it ploughed through all this debris, and it did two things. One is it just scattered all the debris that would have normally have gone to form Mars. So Mars ended up being the runt of the litter, very small, and it would have been bigger had Jupiter not ploughed through the air and created the asteroid belt. But it probably stole a lot of material away, because remember these super Earths, there's more planets out there, about 1.3, 1.4 times the size of Earth than there are Earth-sized planets. So super Earths are more common than Earth-sized planets. That we might have had a super Earth if Jupiter hadn't have ploughed through there as well, and it stole some of the material that would have gone to form Earth. And of course, life would be a lot different. We'd have stronger gravity and so on, so be a lot different. So we probably owe ourselves to Jupiter. But fortunately, Saturn came along, the big brother Saturn came along to the rescue, formed a resonance with Jupiter, and the two of them migrated back out again to the outer solar system. So that's one explanation of why we don't have that. We don't have any in that size there. So why is this gap there? And there's two important clues. One is this, they call it the radius valley, is more pronounced for planets that are really close to the host star, periods within about 100 days. So sort of, we're what, 365, so a third of the distance in. So you tend to see it with planets that are closer to its host star, and the valley is slightly larger for planets orbiting more massive stars. So the general idea is that possibly these more massive stars, we know they do, they have a more intense stellar radiation, really powerful, intense, high energetic X-rays and ultraviolet radiation that would have heated the hydrogen and helium atmosphere around these early rocky planets. They would have naturally grabbed a little bit of hydrogen and helium. Those rocky planets less than about 2 radii, so would have been smaller, less mass, less gravity, close up to these really massive stars, got stripped off their atmospheres. This intense radiation helped shred their atmospheres. So they lost some or their entire atmospheres to become smaller rocky Earths and super Earths. Planets greater than 2 Earth radii, more mass, more gravity, they were able to hang on and retain their thicker atmospheres. So they kept that individual size, nothing happened to them, and they just naturally remained as what they call mini Neptunes. So that's the most likely explanation for that observation. But yeah, just an interesting observation. So implications of what we've discovered, sort of starting to sum up, diversity in the sizes, the orbits, the ages, and the types of planets. It allows vital information to understand how planets form, how planets evolve, how they migrate. You've seen all evidence for that today, and where our solar system fits in with other planetary systems in the galaxy. Now, I touched upon it very briefly, but observing young planetary systems provides valuable insight into planetary formation. Makes sense. You know, the younger a planet is, the more clues there will be there. How did it form? Did it form through accretion, just slowly building up, small pebbles building up to rocks and boulders and just grabbing more and stuff through gravity, or through gravitational collapse in on itself, some just gravitationally unstable within the disk and it collapsed, or was it a combination of the two? These are the sort of stuff that they can tease out through analysing young planets. And I'll pose this question to you now, if anyone can answer it. What is the difficulty in observing young planetary systems though? Young stars tend to be very violent and very active, and that's why as soon as you start, you're getting your data's getting messy. They're getting better at getting computer simulations of these younger stars and subtracting out the noise, but that has been a real problem. So let's move on now to summary and implications. What does all this tell us? Okay, so there's 5 key methods for detecting exoplanets. You've got that on your handout. Planetary systems are common. Our solar system is not unique. Exoplanets show diverse types. There's gas giants, there's super Earths, there's mini Neptunes, there's hot Jupiters. There's even things like lava worlds, where you get these, instead of a gas giant really close to its star puffing out into a big hot Jupiter full of steam, you're also getting smaller rocky planets that have just come so close. They're just covered in lava. They're called lava worlds. So there's huge range in the types of these exoplanets that they're seeing. It is confirming theories of how planets form and how planets evolve, including planetary migration. That's how you got these hot Jupiters in the first place. And they mentioned in the video, they said up to 40%, but then now it's they nudged it up, possibly up to 50% of sun-like stars may potentially host habitable rocky planets, perhaps Earth 2.0. So, once again, this is the message I said at the start. If there's one message you take away from today, it is this. The sky is filled with a diverse range of planets, some of which will be Earth 2.0. I hope you've enjoyed the search for Earth 2.0, discovering planets beyond our solar system. Thank you. So we'll take some questions. Next month is even going to be more exciting. So you've only got 30 sleeps, so get the calendar across, the first one off tomorrow in the morning. We're going to be looking at where should we be looking for types of planets? What should we be looking at? And we're going to look at the origins of life, how life likely got started on Earth, what makes up life. We're going to define life. And what telltale sign life gives. I've given you some homework just to have a look, either Google or ChatGPT, just something to think about. Go home and identify. There's something listening to a talk and then going home, do some homework. Get 6 exoplanets you find interesting, and then look further into it. How were they detected? And here's a question I pose for you. How does carbon dioxide level in a rocky planet's atmosphere tell us? That's your homework to find out. It does. They could pick up the amount of CO2 in a rocky planet, and for an ice giant for that, or a gas giant as well. That actually gives them important clues of the planet formation process. So that's food for thought. So any questions?